Welcome, and today we are going to be talking about heat sinks. In short, heat sinks provide an efficient path for heat to be transferred from an electronic device to ambient air. They do this by increasing the surface area in contact with the air, providing more area for the hot device to transfer energy to the cooler air around it. Some of the most commonly recognized heat sinks are board level and VGA versions, like the examples I have here. The concepts behind heat sinks are incredibly straightforward and their usage is not too much more complicated. So let's jump right into it and talk about what to consider when deciding whether or not you even need a heatsink and how to size your heatsink if you do. There will be some math required to do this, but only basic addition and multiplication, so nothing to worry about. Let's work through the process using an example and assume we use a TO220. These through-hole packages are often used in power electronics for three-terminal devices, such as transistors. The TO220 has a silicon device encapsulated but with a metal baseplate here that is sometimes used for ground connections, and also provides an excellent point on which to mount a heatsink. It should say in the datasheet exactly how the metal plate is connected electrically, which I highly recommend you look into. A critical portion of these calculations is thermal impedance. Thermal impedance is just the measure of how easily heat can transfer from one point to another. The lower the number, the easier heat is transferred. This is typically measured in degrees Celsius per watt, which tells us how many degrees warmer, in Celsius, a junction will get per watt of power dissipated. With each device, you should have access to a datasheet that will provide you the value of the different thermal impedances between junctions. Without a heatsink, the junction between a TO220 device and ambient air can be upwards of 70 degrees Celsius per watt. For our example, we'll assume that our package has a junction to ambient thermal impedance of 55. Again, this means that the junction temperature will increase 55 degrees above ambient temperature for every watt of power dissipated. Let's establish the rest of the assumptions and then do the math. We'll arbitrarily say we need to dissipate 2.42 watts. Our ambient temperature will be no greater than 60 degrees Celsius, and we need to keep the silicon below 125 degrees Celsius. Now, those numbers are all we need to figure out if our TO220 device will get too hot without a heatsink. We simply multiply the watts dissipated by our thermal impedance, or 2.42 watts by 55, which gives us 133.1 degrees. Add that to our ambient temperature of 60 degrees, and we get 193.1 degrees Celsius, well above the required 125 degrees. So that isn't going to work. Now, using that same math in a different direction, we can figure out how much we need to drop the thermal impedance path to keep us in safer temperatures. So let's go backwards. We can have no greater than a 65-degree rise, and in this sample, we can't drop the power requirements. So a 65-degree rise divided by 2.42 gives us 26.9 degrees Celsius per watt. Now, we will round that down to 26 to give us a little cushion and give us less decimal points to worry about. Unfortunately, the addition of a heatsink complicates things because there are now more junctions to worry about. Fortunately, it only requires some addition to add the impedances together. Instead of just worrying about the device to air junction, we need to know the silicon to case junction impedance, case to heatsink junction, and finally the heatsink to ambient air. The silicon to case junction impedance will be provided by your device datasheet. It's typically between 0.5 degrees per watt up to 4 degrees per watt. Let's say 0.5 degrees per watt for our example. The case to heatsink impedance will be based on the thermal interface material, or TIM, which is the typically gray paste that smooths the very small imperfections in a surface so that the tab on the package and the heatsink have optimal surface area contact. This is dependent on both the thickness of the TIM and the surface area of the contact. On this, we'll just skip the details and assume the TIM thermal impedance is 0.5 degrees per watt. Finally, the heatsink to air thermal impedance will also be found in the datasheet, which for this sample, we find that this heatsink with no fan blowing air over it is 14.36. Now we have the thermal impedances of all three junctions, which we can now add together. The sum of these items is 0.5 plus 0.5 plus 14.36, which gives us 15.36, and is well under our maximum value of 26 required. Looking at these results, we could either choose a smaller heatsink or leave it alone. It is good practice to leave some headroom so you don't approach your temperature limit, if at all possible. Just a quick calculation of the performance we should expect with 15.36 degrees Celsius per watt, you would get 2.42 times 15.36 degrees per watt to see a temperature increase of 37.2 degrees over ambient, which, as a reminder, is 60 degrees. So if our assumptions all hold up, we should never go over 97.2 degrees Celsius. You can see how the addition of the heatsink significantly drops the thermal impedance and keeps the device much cooler, well below the 125 degree threshold mentioned earlier. Heatsinks can be the difference between failure and success, and if you don't need a heatsink, don't just make that assumption. Running the numbers on whether or not you need a heatsink is a straightforward process whose most time-consuming step is finding those values from datasheets, and you will greatly increase your peace of mind if you do the calculations. If you have any questions or want to learn more about heatsinks, check out our thermal management blogs on CUIdevices.com.